major reaction to do before the end of term, I guess. So we'll try to get those done today. Yeah, we'll try to get those. Actually, there's two reactions I kind of want to do. We'll get those done today. So Thursday, hopefully we can just do review sort of thing. Just one last thing to finish off the electrophilic aromatic substitution reactions with, and that is what happens if you've got two groups on your ring. And so let's say we've got a hydroxyl group, and then let's say we've got a nitro group here. And we're going to do a bromination reaction. So we're going to react this with bromine and iron tribromide. So the hydroxyl group, the oxygen, the ether, I should say, is going to direct here, here, and of course, right where the nitro group is there. So that one doesn't really count. So I'll just erase this one for the time being. Oh, I didn't mean to do this, but it looks like I did do this. And the nitro group is going to direct meta. So actually, it's going to direct in exactly the same two places. So your product is going to be those two potential products here. I wasn't thinking when I drew this. So one would be the bromine here, and the other one would be the bromine para. Okay, so in this case, they both reinforce one another. That wasn't what I was trying to do. Let me do it. Let me try again here. It feels like Monday. Okay, so let's do this one. Okay. Okay, let's reboot this. Okay, so the oxygen is going to direct here, here, and here. And the nitro group is going to direct here and there, which is covered. So the group that's going to win out is the donating group. So in this case, one's a orthopara director, which is the donating group, and one is the electron withdrawing group, the meta director, which is the nitro group. So in this case, it's going to be the ether. If you've got two groups that donate orthopara, so here's a good example here. So let's pretend that we had a ether again, and we had a bromine here. So the ether is going to direct ortho and para there, and the bromine is going to direct ortho and para here. But remember the bromine is, it's one of the deactivate, when it comes to its, the speed of the reaction, it is slower. So bromine is an ortho-para deactivator, whereas OR is an ortho-para activator. So that would mean that it's the more powerful donating group because it's the activator. So the OR group is going to win out. So in this reaction, if we were doing, let's say we were making, doing a chlorination, then our product would be as the major product. So it's, so that's kind of neat. And that this basically leads to the last little bit for this section, which has to do with like synthesis type questions. So let's pretend that your starting material is a is benzene, and you wanted to make or you wanted to make these two compounds. The way your the order which you put your substituents on is going to become super important, because one substituent might donate or might direct in one direction and the other would direct in the opposite. So for example, if we were doing this and we decided, okay, the first thing we're going to do is we are going to put on the bromine. We would have put the bromine here. This. If we decided to put the nitro group on, remember there was no way to put NH2 on. We had to put the nitro group on and then reduce it. And I think the reducing agent was tin dichloride with a bunch of acid. And then we would do a basic workup. We would this puts the nitro group here. Then for the next step, I'm going to move these over. If we did the nitration, HNO3, then the bromine here is an ortho-para director. So, and we want the para, so we're just going to put that nitro group right here. So now we've got the bromine and the nitro group being para, which is, but if we did it the other order and we did the bromination second, now the interesting thing is that this nitro group is going to be a meta director. Meta. Over here. Then, so what's going to happen is our product is going to be and we've got two completely different, got two different diastereomers here. One's ortho-para, one's para, one's meta. And then the last step would be the reduction in each case. So we would use the tin dichloride with acid. So yeah, when it comes to little syntheses around the rings, the order which you put the various substituents on is super important. But it's a fun little puzzle to solve if we wanted to wanted to do some sort of puzzle solving. So for example, if we wanted to if we started here and we wanted to make how would we do this? So if we do an analysis of our final product, if we were to work our way backwards sort of thing, you will see that the chlorine here, this is a, whoops, that's not what I want. This is ortho. It's the orthopara director, and our alkyl group over here, this is also an orthopara director. Ortho. So how do we go about doing this? Well, the interesting thing is that the straight chained alkane can actually come from, remember, this is the Clemmensen reduction, would come from this group here. So the Clemmensen reduction was the zinc and the mercury and the acid. Now, this group which is on here, this one is the meta director, right? This is the meta. So if we put the chlorine on first, it's going to put that carbonyl group in the wrong place because it would want it to be para. So we have to put on the meta directing group first. So our first reaction would be the Friedel-Crafts acylation reaction. To make this. And then our second step would be the chlorination reaction to put on the chlorine. If we did it in the opposite order, we would run into issues because the chlorine would make, if we did this in the other order, Cl, Fe, Cl3, we would put our chlorine on. But then our next step with the Friedel-Crafts, what we end up with is it's in the wrong position, right? So this would be, if we were trying to do the other thing, this would be wrong. So yeah, the order, the way that things work is kind of important for, so it's fun little, I'll probably, I think on the Moodle page, there's some, on this section, there's some, try some little mini syntheses with these sort of groups, and just keep that in mind, that the order is important, and sometimes, like in this case of up here, the directing group can be converted into a different functional group, which is exactly the opposite type of director. So just make sure that that you keep it in the form that you need it for at the start to direct in the position that you want. So you, like up here, you wanted this group to direct meta, so you didn't reduce it immediately, because if you reduced it immediately, it would be directing orthopara. So yeah, just keep that sort of thing in mind. But yeah, that's basically the section on like electrophilic aromatic substitution reactions. So it's kind of, at the end of it, it's kind of neat. I don't know if anyone had any questions on anything. Okay, well, if not, then there's basically two reactions. Oh, maybe there is one. Sure. Okay, so let's do let's see here. What's a good example? Let me see here. I'm trying to think of a nice, ingenious one. The hamster is running around slowly in my brain this morning, so I don't have an ingenious one here. Let's see. Yeah, let's do this one. Okay, so is the order important for this one? Okay, yeah, try to do the synthesis of this molecule here on the right-hand side. Take a couple seconds to devise a little scheme as to what would be, what would work the best. There's probably a couple of routes that will work, but there's probably one which is slightly better than the others from a practical sense. So let's work our way backwards. We'll do it in 3 different ways. Okay, so let's do one where okay, so in the top one, we are going to break off the benzene. I mean the bromine. So in this case, we would have, let's put it like this. And this would be bromine. Let's do purple right here. And so this would be and green over here. Okay, now of these, that would be the first step. We're working backwards. I guess we could do some other ones. Now, which one of these do I like the least? And which one of these do I like the best? Okay, so if we look at the purple route, you'll notice that that the bromine here will direct orthopara, which would be here and here, and the nitro group would direct meta, which would be here and here. So both of the groups are reinforcing each other. So the chlorine would go in the correct spot. In the green route, the bromine's gonna direct here and here, whereas the chlorine is going to direct here and here. The bromine should win because it's less electronegative than, say, the chlorine. But there is that competition there. So that's part of the issue with the green route. The green route does have an advantage, though, which we could talk about in a second. Now, if we look at the orange route here, the nitro group is going to direct here. And the chlorine is going to direct here, here, and here. So the chlorine is the directing group, so it should prevail, and it would put it in the correct spot. But there's still a bit of competition going on there. So if we were to go back with the purple one, because it's got both of them directing in the same direction, then the best choice, the group we would have to remove next is the nitro group. Because that nitric acid, the bromine directs ortho and para, so it would direct here, here, and here when you want the nitro group there. If you disconnected the nitro group's going to direct meta, so it's going to put the bromine in the correct so if we wanted to do this, it would have to start, you add your bromine first, then you add your nitro group, and then the chlorine. So that route doesn't involve any competition at all. So that's relatively useful. The only disadvantage to this route is that I think this is actually probably the best way to go. The second best way to go is probably the bottom route, is the green. You could choose the bromine or the chlorine. Probably you put the chlorine on second because it's more electronegative. The top route is probably the worst because you would have to put the nitro group on first. and then add the chlorine, FeCl3. And the trouble with that is that the nitro group is such a strong electron withdrawing group, it's going to make all the other reactions really, really slow. So the chlorination reaction would be slow, and then the bromination reaction would be slow as well. So that's the issue with the top one. You have this really powerful group, which is going to slow everything down. And that would be a little minor problem here, but that's only one step, so it's not the end of the world. But anyway, that's sort of a little, one route I think is the best route out of all of them, because it doesn't involve any competition, and that's the one we did right here. So if you had this one, that is excellent. Solving little fun puzzles is always good. All right. So let's see here. There's one thing I need to start. And that is, like, there's two main reactions that are left to do. One is what we call a nucleophilic acyl substitution reaction. And you did this this is one of the labs you did actually. And so what we are dealing with here is basically an acid chloride or similar functional groups that are slightly less reactive than the acid chloride. And the other ones that are commonly used, I guess the common one would be this. So this is a acid chloride, and this is a anhydride. And so what's going on here is that if you've got your acid chloride, well, and you have some nucleophile, the substitution part is that your nucleophile attaches to the carbonyl group, and you lose your chloride. So this is basically the leaving group. And your nucleophile can be, the most common ones that we'll talk about are basically oxygen and nitrogen. So if it's oxygen, it could be like an alcohol. If it was nitrogen, it could be an amine. And so your products, if we were to, so your alcohol, oops, what's happened there? Your alcohol is going to be converted into an ester. Oops, can't spell. And your amine is going to be converted into a amide. And these are both really important functional groups in biochemistry and stuff. And a lot of the reactions in biochemistry are technically nucleophilic acyl substitution reactions. So of course they're mediated in the body through enzymes and all this sort of fun stuff. But it's part of what goes on. So we should at least talk about this a little bit. And of course, these are methods of making important functional groups that we've seen earlier on in the year. So the mechanism's really, really easy. So let's do that. Mechanism. So if we think about our acid chloride, this is a very reactive sort of functional group because we've got the oxygen pulling electron density in one direction, and we've got the chlorines, remember that's electronegative, so it's pulling electron density as well. And so this makes this little carbon here, I'll call it delta plus plus. So it makes it really electrophilic. And so if you've got a alcohol, for example, HR, the oxygen will come in and attack, and those electrons will move on to the more electronegative oxygen atom. So the first step here, we are going to form actually this sort of intermediate here. So, and I've drawn it as a tetrahedral intermediate because this is the tetrahedral intermediate. Now, the other thing which is often in this reaction, particularly if it's a reaction with an alcohol, is something like our friend triethylamine or pyridine. So a Lewis base that can grab acidic protons. So this tetrahedral intermediate is going to break down. And so when it does, it's got really two choices. Those electrons are going to come back down. If we send the alcohol on its way, this would be just the reverse reaction. So that's why I do that little arrow in red. If we eject the, let's use blue. If we eject the chlorine, so chloride, I guess, then we end up with this. And our, say, pyridine can come and grab that proton really quickly. The reaction will effectively be over and done with. So you'd have protonated pyridine, if that's what you used, plus chloride floating around. And depending upon the solvent, these could crash out of the solvent as a salt, as a pyridine salt, but you've made your ester. So yeah, it's the key point here is that when this oxygen attacks, the bond that's broken is the pi bond. So we're breaking the pi bond. We're not breaking this sigma bond to the chlorine first. And we sort of know why. Remember, if we think back to our substitution reactions. So if I was to draw, let's draw this out. So here's our, so this is the acid chloride. Actually, I should draw it in a different perspective, shouldn't I? Yeah, let's draw it like this. So here's our pi bond, pi bond, pi bond. When we are doing our substitution reactions, our SN1, sorry, our SN2 and SN1 reactions, remember where the little, if we were breaking this sigma bond, the sigma star, if we wanted to break the sigma bond here of the leaving group, remember where the sigma star was? It was here, sigma star. So the nucleophile really can't get into there to attack that sigma star. It's not the lowest orbital to attack. It's difficult to get in there. So the orbital, the easiest one to break first is the pi star. So your nucleophile can come in and attack the pi star, form a tetrahedra intermediate, and then when the electrons come down, they can go into the sigma star of the chloride to eject it out. So I guess the key part is that the nucleophile breaks the pi bond, and then the pi bond reforms at this stage right here when you're booting out the chloride. So the chloride leaves. So yeah, the main important thing is that it doesn't attack. It's not just, we don't draw this mechanism like this. That's a big sort of, that's a big no-no. So, but okay, so it's really, and so for all of these reactions, it's exactly the same little mechanism. So that's the neat little bit here. So if we did the same reaction with an amine, say let's use secondary amine here. When you're doing a reaction with an amine, you don't necessarily need pyridine or triethylamine. You could sometimes just use two equivalents of whatever amine you're using, one to act as a nucleophile and one to act as the base. So here we would have these lone pairs, they attack, the electrons move up. Then the electrons move down, we lose our chloride. Stop that. And other amine comes and deprotonates this. It doesn't matter if you deprotonate the amine, or this would be, in this case, the amide right here, or if you were to actually do it at this stage, like if I was to draw the amine come in and if I was to draw that at that stage, either one of those is fine as far as I'm concerned. The thing which doesn't happen though is we don't make this first and have that attack the acid chloride, because remember, this is super basic, and so that isn't gonna happen. And likewise over here, like the triethylamine isn't really strong enough to deprotonate the alcohol at the start, or the pyridine isn't strong enough to deprotonate the alcohol at the start. So it really is the alcohol which is attacking, not this. It's not the alkoxide, it's the alcohol itself. So those are just but it doesn't matter if you deprotonate this nitrogen at the tetrahedral intermediate stage. It probably doesn't happen then. It probably happens at the very end, and this would happen really fast. This would be fast. As long as the key point though is not doing it at the very start, because that isn't going to happen. The base isn't strong enough to deprotonate that nitrogen. But anyway, that's basically, this is the nucleophilic acyl substitution reaction, and there's a few examples that, so I'm using an acid chloride here. There are other groups that could be used, as long as you've got like this, what this really is, for lack of a better term, is that we've got leaving group here, LG. Life's good, leaving group. So when I drew that anhydride at the start, the top, if we have our sort of alcohol attack that, nitrogen attack, sorry, lone pair attacks, the electrons move up onto the oxygen to form the tetrahedral intermediate. The electrons come back down to reform the bond, and we lose our leaving group. So our product is going to be and our leaving group is the carboxylate anion, which is stabilized by resonance. And so that, or triethylamine, will then grab that proton, and then you've got your final product. So this, what I've sort of highlighted here is the what textbooks show as the arrow movement. The electrons move up, electrons move down, you lose your leaving group. Rather than, some people are lazy, they don't want to draw the tetrahedral intermediate, say here. But as long as you know that there's a tetrahedral intermediate, then that's super. So what we'll do is, because class time is effectively over, at the start of next class, I'll do a couple more of examples of this, just to, you know, so everybody knows, I guess. And then after that, we'll do a bit of a, I guess we'll do a little bit of a review for the final exam, since next class is our last class together. Yeah, but anyway, this little reaction is, yeah, we'll do some more examples of it. It's a neat little reaction to do, and it's quite important for where you guys are going in the future. So that's why it's sort of, I need to cover it a bit. All right, so I guess unless there's an immediate question, I guess I'll see everybody on Thursday. All right then. Well, have a good couple days.